let's proceed with the chapter 25. We will finish it today, inshallah, and we will start solving some problems from chapter 25. Okay, so remember that in the previous lecture we introduced the concept of or we determined how much energy is stored in a capacitor if it has a charge Q and it has so we remind you okay, so we said the potential energy, that is electric potential energy that is stored in a capacitor, is equal 1/2 C delta V squared. Okay, we can also use this is since we know that Q is C delta V, this is also equal to 1/2 Q squared over C, and it's also equal to 1/2 Q times delta V. So you can use any of these equations in order to determine the potential energy of a capacitor or stored in a capacitor, electric potential energy. And we also determined the energy density, which is energy per unit volume. So small u is the energy density, capital U divided by the volume, so this is volume. Okay, and we found that this is 1/2 epsilon 0 the electric field squared. And we said the electric potential energy, actually this is a general equation that applies in any electric energy, any region of space. If you have the electric field, you can determine what is the energy per unit volume of that electric field by dividing or by using this equation, 1/2 epsilon 0 E squared. Okay, we solved a number of problems, and I would like to remind you that about the when you solve problem, you have to always look because usually you might have a problem statement where we are changing the condition. So, for example, we connect a capacitor to the battery, and then we disconnect from the battery, and maybe we do something. Or you keep it connected to the battery and then you increase the separation or reduce the separation and so on. So when you solve problem, you have to ask yourself always, is the capacitor connected, does it remain connected to a battery or not? Because a battery will always maintain a constant potential difference across its terminals. So it will provide a constant voltage, ideally. Yeah? We know in real life the battery voltage decreases in very small amounts, and after some period of time you have to change the battery or recharge the battery. Okay. However, so you have to keep in mind the battery will always maintain the delta V to be constant. If you disconnect a capacitor from the battery, okay, and in that case the potential is not going to be the same, but the charge is going to be the same. The charge is maintained unless we connect the capacitor to another circuit. Okay, then it will discharge through the other circuit. So in a problem, so that's why you must note whether the modification of the capacitor are being made while the capacitor is connected to the battery or after it is disconnected from the battery. If the capacitor remains connected to the battery, the voltage across the capacitor necessarily remains the same. Okay. If, however, you disconnect the capacitor from the battery before making any modification to the capacitor is an isolated system for electric charge and its charge remains constant. Okay, so in one case delta V is constant when the battery is still connected. In the other case, we have the charge is constant. So keep in mind when you solve problems. All right, so let me go to the presentation mode and introduce the next topic. Okay, so far we have studied capacitors where we have two conducting metal plates, or they can be cylinders or spherical shape, but in between them there is air or vacuum, because air is an insulator and so is vacuum. But however, in reality, usually capacitors that we use, they have a dielectric material. They have an insulating material that is inserted between the capacitor plates. So usually we insert what we call a dielectric, which is an insulating material between the two plates of the capacitor. So it can be a plastic, usually a plastic, but it can be other like oil and so on. Okay. Now, the capacitance in that case will increase, and it's going to be given by the kappa times C. Kappa is what we call the dielectric constant of the material. So different materials have different dielectric constants. So we multiply. So if you replace the air with a dielectric material with a dielectric constant kappa, the capacitor becomes equal to kappa times C. The kappa is for air and vacuum, it's almost 1, but for other dielectric materials, it's always larger than 1, as we will see. So for vacuum, it's 1. For air, it's 1.0005. Paper, it's 3.5. Water, 80.4. And strontium titanate is 310. So you can see, by introducing strontium titanate, you can multiply the value of the capacitance all 310 times. So if you have 1 microfarad capacitor with air, if you just replace air, keeping the same distance with this dielectric material, you can have a large capacitance. And obviously, if you have a large capacitance, that means you have a larger charge, a larger energy you can store in that capacitor. There are a lot of people doing research how to increase the capacitance or the storage capability of a capacitor, because capacitors are used in many devices. They don't want them to be very big because they will take a lot of space. So they want the capacitor to be small, okay, yet they have high energy storage. So one way of doing that is by using materials like strontium titanate. Okay. So let's speak about Faraday's experiment. Let's assume we have a capacitor connected to a battery. Okay, so let's assume the charge that accumulates is Q1, capacitor C1, and the battery voltage is delta V. Okay, and then what we do, we introduce. This is what Faraday did. He introduced between the two plates of a capacitor dielectric material. Okay. And he looked at what happens to the voltage, okay, or to the charge. Okay, so we know here the charge Q1 is equal to C1. Let's say that this voltage here is delta V. Okay. Now the battery is still connected, so the potential difference is still delta V. Okay, but now the charge Q2 is going to be equal to C2 times delta V. And since C2 is kappa C1, kappa, I always have problem writing a kappa. Okay, so kappa C1 times delta V. So you can see that in this case, the charge has increased. So Q2 is larger than Q1. In fact, it's multiplied by kappa. So the higher the dielectric constant you put, the higher the charge you will be able to accumulate in this capacitor. Okay? So, this is what we just have done. Q2 is equal to kappa Q1. Okay? Now, let's assume you charge a capacitor, okay, and then you disconnect it from a battery. So now we are connecting it to a voltmeter. A voltmeter is just an instrument that measures voltage, okay? And usually it has a very high input impedance, so it does not affect the circuit. We use it to measure the voltage. Okay, so let's assume we have a charge. Let's call this charge Q1. Okay, and then we introduce, and this is what also Faraday's experiment. So he disconnected from the battery. Okay, so he has a charge stored after connecting to the capacitor to the battery. It has a charge stored. You disconnect from the battery, we know the charge will remain there, and we have a potential difference equal to that of the battery. Then what he did, he introduced the electric material between the two plates of the capacitor, and he looked at what happens to the voltage. And he was surprised. He found that the voltage actually decreases. Okay, so let's look at the what is really happening. Okay, so here we have the let's calculate delta V. Let's call it delta V1. This is going to be equal to Q1 divided by C1. Okay. After you introduce the electric, and since the battery is not connected anymore, the voltage does not remain constant, and so we can get delta V2. Okay, delta V2 is going to be equal to Q2 divided by C2, which is kappa C1. Now the question is Q2 equal to Q1 or not? Is the charge conserved here? Yes? No? Yes. So here the charge is conserved. We said the voltmeter does not affect the circuit, so normally the charge is conserved. So let's assume there is no charge being lost to the voltmeter. So this is equal to Q1 divided by kappa C1, which means this is equal to delta V1 divided by kappa. Remember, kappa is a number that is always 1 or larger. For the electric, it's larger than 1. So obviously, that was a surprise. So here, the capacitance increases. Okay, if it's connected to the battery, the charge increases. But if you disconnect from the battery, we observe that the voltage decreases. And this is why, because delta V2 is actually delta V1 divided by kappa. So this was a very interesting observation that Faraday did, and so again delta V2 is just less than delta V1 in this case. Okay, so always remember, when you make any changes to the capacitor, like here you are introducing a dielectric material between the plates of the capacitor, you have to ask yourself, is the battery connected or not? If the battery is connected, that means the voltage is going to be the same, the charge can change. If you disconnect the battery and you introduce a dielectric, the charge is going to be conserved, but you can see the voltage is not going to be the same. It will change. All right? So, now, in the video I have showed you 2 lectures ago, you have seen that as the voltage is increased between the 2 aluminum foils, and there is an insulating material between them, we start hearing and that's due to the breakdown of the material that is between the 2 aluminum plates. So in order to operate a capacitor without breakdown, you have to maintain the voltage difference across its plates lower than a maximum voltage. There is a maximum voltage that we call the breakdown voltage. Okay. So if you exceed that maximum voltage, you will have breakdown, meaning that you will have conduction through the dielectric material, which is supposed to be an insulator, like air. Air is supposed to be an insulator, but when you have clouds accumulating, you can exceed the maximum electric field of the air, and you can start having conduction through the air, which is supposed to be an insulator. But so it stops becoming being an insulator, and it starts conducting. So there is a breakdown or a conducting path, and hence electrons will move from one plate to another, and the energy stored in the capacitor will be lost. So the main purpose of the capacitor in most applications is to store energy and use it for something. If you exceed the maximum voltage of the material that you have, then you lose the capacitor, and you will have a breakdown of the capacitor. Sometimes the damage might be permanent, so the capacitance you have to throw it. But so you should always try to operate the capacitor below the maximum limit of the voltage. So the electric strength of a dielectric is the maximum electric field it can tolerate without breakdown. So obviously, if we have delta V and we have a separation D, the electric field magnitude is delta V over D. Okay, so this has to be lower than a maximum value, and that's what we call the dielectric strength. The dielectric strength is the maximum electric field it can tolerate without breaking down. Okay, so let's look at some typical values. For air, the maximum electric field that it can withstand without breakdown is 3000 volts per millimeter. It's quite high, 3000 volts per millimeter. If you introduce paper between the two plates, it increases to 16,000 volts per millimeter. And strontium titanate, you can increase the voltage to 8,000, the electric field to 8,000 volts per millimeter. That's a very strong electric field. So usually you can operate them safely as long as you do not exceed the breakdown. So here is a table of many elements starting from air, which has a dielectric constant of 1. Notice the other, all the kappa values are higher than 1. Vacuum has a value of 1. But notice what happens to the dielectric strength. This is in million volts per meter. So for air, it's 3 million volts per meter. But you can reach, for bakelite, for example, you can reach, or polystyrene, you can reach 24 million volts per meter. Okay? All right. So, what is the new equation for a capacitor? Previously, we said capacitance is C, is epsilon 0 A over D for parallel plate capacitor. Okay. Oops. Okay, I lost my pen. All right. So the new value becomes kappa epsilon 0 A over D. So you multiply basically epsilon 0 in any of the equations that we have seen before. If you multiply epsilon 0 by kappa, that's the new value. So we spoke about the dielectric strength, which is the maximum electric field you can apply without breakdown. Okay, and the breakdown voltage, if you exceed that voltage, you will have a breakdown and you lose the charge in your capacitor. Okay, so insulating materials, they always have a kappa larger than 1, except obviously air and the vacuum. Okay, and usually we use a dielectric material. We don't use air or vacuum because first of all we increase the capacitance, hence we increase the how much charge and energy we can store. We increase also the maximum operating voltage because the breakdown, the dielectric strength is much stronger for other materials compared to air, and also for mechanical strength. So when you put something between the two plates, the chances of damaging or bringing the plates closer is much less than having air. Okay, so in all of the previous equation we have seen, in order to handle the electric materials other than air or vacuum, whenever you have epsilon, which almost all of the equations we had before had epsilon, whenever you have epsilon you have to multiply it by kappa. Okay, so let's take an example. Remember, for a point charge, this was the electric field. We found that the electric field, Coulomb's law says it's K is 1 over 4 pi epsilon 0. So let's forget about K. Let's use 1 over 4 pi epsilon 0. So it's Q divided by 4 pi epsilon 0 r squared. Now this charge is in air or in vacuum. How about if it's in a dielectric material, like strontium titanate? So if it's in a dielectric material, the equation is the same except we multiply epsilon 0 by kappa. So the new equation becomes Q is, or the electric field is equal to Q divided by 4 pi kappa epsilon 0, not epsilon 0, kappa epsilon 0 r squared. So this is, so starting from Coulomb's law, the electric field, potential energy, the potential, all of the equations, whenever you have epsilon 0, if you have a dielectric material rather than air or vacuum, then you have to do that. So let's look at some of the equations here. So for example, remember, for a perfect conductor or a conductor, we determined the electric field just outside the surface, and we found we used Gauss's law we found it's equal sigma over epsilon 0, the electric field, and you just outside the conductor. So this was the equation. Now, if the conductor is within an insulator that has a dielectric material kappa, so now we have a dielectric material instead of air, then the electric field is sigma over kappa epsilon 0. So do not forget this, because so if you're given a problem where you're told instead of air we have another insulating material, remember always to multiply epsilon 0 by kappa. So let's look at the equation. So this is capacitor, epsilon 0 over A, it becomes kappa epsilon 0 over D, kappa epsilon 0 A over D. This is Coulomb's law. It's Q1 Q2 divided by 4 pi epsilon 0 R squared. It becomes Q1 Q2 divided by 4 pi kappa epsilon 0 R squared. This is electric field. We have seen this. Okay. This is the potential energy. Remember, the potential energy, if you have two charges, Q1 and Q2, separated by distance R, we determine it's equal Q1 Q2 divided by 4 pi epsilon 0 R. So this becomes, if the two charges are within a dielectric material, it becomes Q1 Q2 divided by 4 pi kappa epsilon 0 R. Okay, this is the potential due to a charge. The potential due to a charge, we determined it's kq over r, or 1 over 4 pi epsilon 0 q over r. Again, if we want to determine inside a dielectric material for a point charge, it becomes q divided by 4 pi kappa epsilon 0 r. This is Gauss's law. The flux, which is the electric field dotted with dA, is equal to the charge enclosed divided by epsilon 0. The Gauss's law, if now you are not in air, you are in a dielectric, becomes Q enclosed divided by kappa epsilon 0. This is Gauss's law. Okay, so we have seen this. This is the electric field outside the conductor. And last but not least, the potential energy, the energy per unit volume, or the energy density, we said it's 1/2 epsilon 0 in the electric field, the magnitude of the electric field squared. It becomes 1/2 kappa epsilon 0 times the electric field. Remember, the electric field is also a function of epsilon 0. For example, the electric field outside the conductor, in air it's sigma over epsilon 0, but in a dielectric material it's sigma over kappa epsilon 0. So you have two things that you have to worry about. You have to multiply kappa epsilon 0 here, multiply epsilon 0 by kappa, but you have to remember the electric field, if it's a function of epsilon 0, and usually it is, then you have to multiply epsilon 0 by kappa. So this is the most tricky part, as we will see. Okay? All right. So here is a problem. We have the capacitor C1 connect to a battery with a potential difference of 12.5 volts, and then we disconnect the battery. Okay, we disconnect the battery, then we insert a dielectric material, and the question is, what is the potential energy before and after the insertion of the dielectric? Okay, let me see if I still have intro. Scott, see if I recovered my pen. No. Okay, so let me, I hate to do this, but I have to. Okay, so before and after insertion of the electric. We know the equation for potential energy. Let's see if the pen works. Okay, yes. Okay, so we can use any of the three equations. So here we have the capacitor and the delta V, so we can use 1/2 C1 delta V1 squared. Okay, let's call this U1. Okay, then we disconnect the battery. So when we disconnect the battery, the voltage does not remain constant. How about the charge? The charge remains constant. We said because we are not connecting. So let's see Q1 here. Q1 for this, the charge that is on capacitor C1 is just equal C1 delta V1. Okay. Now we want to determine the potential energy in the second case. We don't know the voltage, so what we can use the other equation, which is 1/2 Q2 squared divided by C2. This is the second equation. But Q2 is equal to Q1 because we have conservation of charge. So I can write this is 1/2 of Q1 squared divided, what's C2? C2 is kappa C1. So C2 is kappa C1. So this is kappa C1. So notice that this is actually equal to U1. So this is equal 1 over kappa times Q1 squared divided by 2 C1, which is U1. So this is U1 divided by kappa. So notice that the energy, when we put the dielectric, the potential energy is actually less. So in the previous case, it was equal to, we will see the numbers. In the second case, it's divided by kappa. So we have less energy storage in this case. So let's look at the numbers. So for the first case, you have 1055 picojoules of energy, electric potential energy. But after you disconnect the battery and introduce the dielectric material, it becomes 162 picojoules. So it's almost 1/5 of the previous one. A big loss of energy in this case. All right. So the next question is, what is the work done by the person who inserts the dielectric slab? Okay. So in this case, remember, work applied is equal to delta U, which is U, the potential energy after, minus the potential energy before. So originally we had the potential energy U1, and after we disconnect the battery and we introduce the dielectric, we have potential energy U2. So when we calculate this, we find that the applied work is minus 893 picojoules. So this is it's a negative because actually the electric field is helping us to put the dielectric between the two plates. So we have to actually do negative energy because the electric field is pulling the dielectric into the space between the two capacitors. All right. So if we are asked what is the work due to the electric field, in this case it's minus. Remember, the work done by the electric force is minus delta U. The work that is applied by an external force is delta U. So this is what we're using here. So we find this is the work applied is minus 893 picojoules, and the work done by the electric field is 893 picojoules. Okay, next question. All right, so now we have a checkpoint. And all right, so let's do it together. Okay, what happens to the potential difference? Now we are connecting a capacitor to a battery. The battery is still connected to the capacitor, and we introduce a dielectric between the two capacitor plates. Okay, so the first thing is, what happens to the potential difference? Anybody? The potential difference. Who says decreases, raise your hand. Who says increases? Raise your hand. Increases. Who says remains constant? Majority says remains constant. Why it remains constant? The battery. Jama'a, please be with me. How many times did I repeat from the beginning of the session? I said, when the battery is connected, it maintains the voltage. I don't want you to be present bodily only. I want you to be present with your brain. Okay? So the battery is still connected, so the voltage does not change. All right? So let's write this. Delta V2 is equal, so let's say this is delta V2, this is delta V1. Okay, delta V2 is equal to delta V1 because battery is connected. Let me write it down. Is connected. Okay? The next question is, what happens to the capacitance? Does the capacitance increase, decrease, or remain the same? Who says it increases? Who says it decreases? Who says it remains the same? It increases. Huh? Many of you are not answering. Yeah? Should we start the Kahoot? Huh? Please participate. Okay? So, what did we say? We said the capacitance now, C2, is kappa C1. And we said kappa is always larger than 1. So whenever you introduce a dielectric, the capacitance will increase. So let's write this. C2 is kappa C1. So C2 is larger than C1. Okay, next question. What happens to the charge on the capacitor? Okay, so some of you are saying increases. Raise your hand if you say it increases. Okay, how about it decreases? Anybody says decreases? Stays the same. Okay, so let's verify this. So here we have Q2 is going to be equal to C2 delta V. Delta V did not change because the battery is connected. C2 has increased. This is kappa C1. So Q2 is kappa C1 delta V. So Q2 is also kappa Q1. So we can see here Q2 is kappa Q1. So clearly the charge increases. Clear? Okay. How about the potential energy? Okay, so let's ask again. What happens to the potential energy? And you have 3 equations for potential energy. Increases. Who says it increases? Raise your hand. Who says it decreases? Decreases. Remains the same? Okay, so the majority are saying it increases. So let's verify this. U2, okay, what should we use? Should we use 1/2 C2 delta V2 squared? But delta V2 is delta V1, huh? So delta V2 is delta V1 squared. Okay, and we know C2 is kappa C1, so this is 1/2 kappa C1 delta V1 squared. So you can see this is kappa U1 squared, U1. Okay, ولا? Because U1 here is 1/2 C1 delta V squared. So that's here 1/2 times 1/2. So you multiply it by kappa. So this is 1/2. And you multiply it by kappa. So you have kappa U1. So clearly U2 is larger than U1. Okay, let me connect my battery first. Okay, so U2, so it looks like everything is increasing. C2 increased, Q2 increased, U2 increased. Okay, how about the electric field between the plates? The electric field. Oops. What do you think will happen to the electric field? Decreases? Okay, who says decreases? Raise your hand. Increases? Stays the same? Stays the same. Okay. What is the electric field? So let's write the electric field here. E1. Okay. This is delta V divided by D. Correct? How about E2? E2 is also delta V2, which is equal to delta V1. So this is delta V1 divided by the same distance. So E2 is equal to E1. Tricky, yeah? We see everything increasing, yet E1 is the same. How about the energy density? Think about energy density. No, think about it first. Think about it. Okay. All right. So, who says it increases? Okay. Who says it decreases? Who says it stays the same? Who says it stays the same? Okay, let's verify this. Okay, so the majority are saying increases, but many are neutral. Okay, so U1, energy density 1, we said is 1/2 epsilon 0 E1 squared. Okay, let's look at U2. U2 is 1/2. Now we have to multiply by kappa because we have epsilon 0. Kappa epsilon 0 E2 squared. We said E2 is equal to E1. So this is equal to kappa U1. Huh? So kappa U1. So this is higher than U1. So clearly it increases. But you have to be careful. Huh? So the trend is E1 are equal to E2, and everybody will say, oh, the energy density is the same. But we have epsilon 0 in the equation. We have to multiply it by kappa. So it has to increase. Okay, I hope this is clear. All right, so I think we did everything correct here. Okay. All right, one last problem, and we will start solving in the Kahoot. A parallel plate capacitor with a plate separation D has a capacitance C0. So this is the initial capacitance in the absence of a dielectric. All right. What is the capacitance when a slab of dielectric material of dielectric constant kappa and thickness Fd? So the separation between the two plates is D. This is Fd. This is the thickness of the dielectric material, where F is a fraction between 0 and 1. So it can be 0.5, it can be 0.2, whatever. Okay, so they want us to determine what is the new capacitance. All right, so you already have here, this is exactly equivalent to two capacitors that are connected in series. Because you can think as if there is a plate here and there is another plate here, they are connected, and you have one capacitor C1 and another capacitor C2. Capacitor C1 has a dielectric material and C2 has air. So we can think about them as two capacitors connected in series, and we can determine the equivalent. So let's first of all determine C1. C1 is the capacitor, this capacitor here. Okay, so it's kappa epsilon 0 A, which is the area, divided by the distance. The distance is now Fd. It's a fraction times D. Okay, what is capacitance C2? C2 has only air. Okay, so we can write epsilon 0, the area, the same area, divided by the distance, which is now 1 minus F times D. So for example, if F is equal to 0.5, in the first case C1 is going to be kappa epsilon 0 A divided by D over 2, and C2 will be also epsilon 0 A divided by D over 2. So 1/2. Okay, now these capacitors are in series, and we said when we combine capacitors in series, we can write that 1 over C equivalent is equal 1 over C1 plus 1 over C2. And we can solve for the equivalent capacitor. So this is going to be equal, okay, so this is going to be Fd divided by kappa epsilon 0 A plus 1 over C2. So this is 1 minus F times D divided by epsilon 0 A. Okay, so 1 over C equivalent, or 1 over C equivalent. We can do the math. So we can multiply the second term by kappa, so it will have the same, so it's going to be Fd plus kappa 1 minus Fd divided by kappa epsilon 0 A. So now we can solve for C equivalent. It's going to be equal, I can take the D outside. Okay, so yeah, I can in fact write. So this is going to be D, so it's going to be kappa epsilon 0 A divided by D times F, okay, plus kappa 1 minus F. Correct? So kappa epsilon 0 A over D is C1. So C equivalent, or C0, is it? Yeah, C0. This is equal to C0, which is the initial capacitance when there was no dielectric, divided by F plus kappa 1 minus F. Okay, so here this is a problem where they did not give us numbers, so you have to solve for the equations. واضح? Everything is clear. Any question about chapter 25? Anything that is shaky? Huh? Question? Shouldn't be? No, we inverted this. So we inverted 1 over C equivalent. So kappa epsilon 0A became in the denominator. In the other term become, the numerator become, so I took D as a, I factored out D. So it's D times F here. And you have kappa 1 minus F times D. So I think the math is correct. You can check it. Let me look at the result here. Is it correct? Yeah, I think it's correct. All right. So let's start solving problems together. Okay, we don't have a lot of time left actually, but it's okay. We have 45, almost 45 minutes, or 50 minutes, 30 minutes. So let me see Kahoot. So take out your pencil and paper, and I want you to work in groups of at least 2, can be 3. I prefer that you solve problems in teams rather than individually. Okay, loading. Looks like the internet is slow today for some reason. Okay, so let's go to home here, home. Extremely slow today. Okay, so okay, so let's play. Okay, so enter the Kahoot, please. Will come up shortly. And so we have the teams. Abdullah Ibrahim can work together, and so please let's work in teams. If you can join the team, please. I prefer you discuss with the other students when you solve these problems. The discussion contributes more to the understanding. It's really slow today. Yes. نعم. لا. No, I think chapter 25, I think. Are you sure? Something like that. Okay, let's see. No, this is chapter 25. Yeah, it's called chapter 24, but it's chapter 25. Thank you for telling me, but I think the name was wrong. But I think it's chapter 25. So enter 413-9623, 413-9623, and let's start the Kahoot. So I hope this is chapter 25. So while you're logging in, let me yes, it's capacitance. Okay, so here, 2 minutes. Let me read for this for you. The plates of a spherical capacitor have a radii 38 millimeter and 40 millimeters. Calculate the capacitance. B, you're supposed to you're supposed to do A, question A. And what must be the plate area of a parallel plate capacitor with the same plate separation? Remember, for a spherical capacitor, it's, I think, 2 pi epsilon 0 times AB divided by B minus A, if I'm not mistaken. Yes, 4 pi epsilon 0 AB divided by B minus A. Okay, so, and if you finish, you can answer the next question. So let me, 1 minute. This is very easy, warm up. One minute and a half. So I always give a warm-up, easy problem. Looks like the long 2 years of COVID-19 made us more individual-oriented rather than group-oriented. I see many of you preferring to work as individuals. Believe me, you learn much more when you work as a group. It's much more fun also. Okay, so choose between A, B, C, or D. Everybody finished? Everybody finished? Raise your hand if you finished. Okay, the majority finished. So let me start. So you have only 10 seconds, You'll have only 10 seconds this time, Oh, 20 seconds. Okay, 20 seconds. 5 seconds. Okay, majority are correct, 21 and 5 incorrect. Probably those who worked in team are correct. And okay, so let's look at the problem. So this is actually straightforward. You just plug in the equation for the cylindrical capacitance. So let's see, this is chapter 25, solution. Okay, so here you just plug the equation, okay, which is, we said, capacitance C is 4 pi epsilon 0 AB divided by B minus A. And when you do that, you find so you have to be careful. The distances are given in millimeter. So you have to convert them to meters and do the calculation. So you find, in this case, it's going to be equal to 84.5 picofarads. 84.5 picofarads. Okay, the next question, what must be the plate area of a parallel plate capacitor? So we know capacitor for a parallel plate capacitor is epsilon 0A over D, okay? And D is the same. The distance between the plates is 2 millimeters, so we need to determine A. So A is just equal C D divided by epsilon 0. So this is 84.5, pico is 10 minus 12, times D, which is 2 millimeter. 2 millimeter is 2 10 minus 3 meters divided by epsilon 0, 8.85, 10 to the minus 12. And when you do that, you find that the area is 191 centimeters squared. Next problem. واضح? Clear. Okay, so we have 59100 leading. All right, so 1 minute and a half for this one. This is also an easy problem. Capacitors in parallel. So how many 1 microfarad capacitors must be connected in parallel to store a charge of 1 coulomb, it's a big charge, with a potential of 110 volts across the capacitors? Attendance sheet وين وصلت يا جماعة؟ Please pass it so that everybody signs. Pass the attendance sheet. And bring it back to me once it's finished. I see a lot of absences today. Okay. So, who's ready? Raise your hand. يلا يا جماعة. نزلت الدسكشن يا عبد الله إبراهيم. Okay. So, choose between A, B, C, or D. Okay, I'll start the Kahoot. Ten seconds. Nice. 19 correct answers and 7 incorrect answers. Okay, let's look at this one. Okay, so here, usually I like to draw. For me, half the solution is drawing. So we have a battery is 110 volts. This is delta V. Okay, and then we connect capacitors in parallel. So let me call this C1, C2, and we keep doing this until we reach Cn. C capital N. Okay, so we are given the charge we want to store. The charge Q is 1 coulomb. How do I solve a problem like this? I determine the equivalent capacitance. Always when you have a problem with a lot of capacitance, try to simplify it. Okay? What is the equivalent capacitor when capacitors are connected in the sum? So C equivalent So C equivalent is just going to be the sum of all of the C's, Ci from 1 to n. So let me call it, this is n times C, correct? Okay, so this is C equivalent, and we know that this is equal to the charge. So C equivalent is equal to the charge divided by delta V. So C equivalent, which is n times C. So we can solve for n, it's just equal to Q divided by delta V times C. So Q is 1 coulomb divided by delta V, which is 110 volts, times C, which is 1 microfarad. Okay, and when we do that, you find this is approximately 990 or 91, I think is closer. So you need 9,090 capacitors, each one of them of 1 microfarad capacitor, in order to store a charge of 1 coulomb. Okay, so obviously it's too big or too many capacitors. Next problem. واضح? So this is just equivalent capacitors. Next problem. So still the same group are leading, and next. Okay, so this is very similar. Okay, I will give you 1.5 minutes for this one. So let me read it. Each of the uncharged capacitors in the figure has a capacitance of 25 microfarads. A potential difference of 4,200 volts is established when the switch is closed. So we have a battery that has 4,200 volts. How many coulombs of charge pass through the meter A? Meter A is a charge meter or an amp meter, or whatever you call it. We want to determine how much charge flows through this. Basically saying how much charge is on all of these capacitors. Okay, so 1.5 minutes. رجعوا لي الاتندنس شيت يا جماعه. Finished? Who finished? Raise your hand. Majority finished. Okay, so choose between A, B, C, or D. Okay, I'll start. And you have 20 more seconds. Okay, so 16 correct answers and 7 incorrect answers. Good. All right, so let's look at this problem. Very simple. It's very similar to the previous one, actually. Oops. Okay, so this is the problem here. Okay, so again, we can replace these by equivalent capacitance, C equivalent. Since these capacitors are connected in parallel, it's the sum, so it's 3 times C, okay, the same voltage. And how many coulombs of charge? We have Q is equal C equivalent times delta V, okay, so this is 3C times delta V, and we find that this is equal to 0.315 coulombs, 0.315 coulombs. Straightforward. So that's how much charge it flows through the ammeter. Remember, when we close the switch, electrons are going to be moving through the ammeter here, and so the ammeter measures current. They will be moving until we reach equilibrium. When we reach equilibrium, that means the potential across all of the capacitors is equal to the potential of the battery. Next problem. All right. Next. Okay, this is a challenging problem, so I want you to answer question B, not C. Question B. There is no C, So let me read it. Okay, we have a figure. The battery has a potential difference of 10 volts, okay, and the 5 capacitors each have a capacitance of 10 microfarads. So all of the capacitors have the same value. What is the charge on capacitor C1? That's an easy one. And what is the charge on capacitor C2? That's a difficult one. So I will give you 3 minutes for this one. 3 minutes.